electric potential at a point due to an electric dipole. Dipole, we are aware, it's a system comprising of two equal and opposite charges separated by a finite separation. We have discussed the term dipole length, dipole moment, axial line, equitorial line. So in this particular section, what we intend to do is, we will find an expression for the electric potential at a point on the axial line of an electric dipole and at a point on the equitorial line of an electric dipole. So let's start with the first scenario. This is suppose the electric dipole. It is a system comprising of two equal and opposite charges. We all are aware of it. This is the center of the dipole and the dipole length was considered to be 2a. So a dipole length, as you remember, it's a vector quantity directed from negative charge to positive charge. Dipole moment, it is also vector quantity. But potential is a scalar quantity. And you are aware this is a scalar quantity. And this is the axial line. Along the length of the dipole, that's an axial line. This is axial line. Suppose there is any arbitrary point where the net potential is to be determined due to this dipole. Put this as 1 and this 2. If the distance is considered to be r from here, actually r is the distance we will consider from the center of the dipole. So, from the positive charge, the distance will be r minus q. While the distance of the observation point P from the negative charge would be, look, this is r and this is a. So it will be r plus a. Okay. Potential being a scalar quantity, in order to determine the net potential at a given point due to a system of charges, will make use of the laws of algebraic addition. So no need to draw vector diagrams, it's a scalar quantity. So V net or V axial, net potential at any point on the axis, it would be equal to potential at point P due to first charge plus potential at point P due to the second charge. So, due to the first charge, formula is kq by r. So k, it's 1 over 4 pi epsilon, charge is q. Distance of this charge at 1 from point P is r minus k. Okay. Potential at point P due to this negative charge. It's a scalar. So if it is negative, you should write here negative, minus q. 4 pi epsilon. What about its distance from the second charge? It's r plus a. So let's evaluate it. Q over 4 pi epsilon. It can be taken as common. So LCM would be r minus a and r plus a. So it will be r square minus a square. And here the term left would be 1 over r minus a minus 1 over r plus a. So r plus a gets over here minus r minus a. Right? Evaluate it. Open the bracket. Plus r minus r get cancelled. A minus 1 plus a, that will give you 2a. So what do you get is q multiplied by 2a over 4 pi epsilon r square minus a square. Do you remember this q into 2a? This is the product of magnitude of either of the charge and the distance between them. And it is known as dipole moment. So in terms of dipole moment, the expression would be P divided by 4 pi epsilon r square minus a square. This is the expression for the potential at any point on the axial line due to an electric dipole. Now look, you can consider special cases as well. Just was in the case of electric field, you have considered special cases for short dipole. Short dipole means when the distance of observation from the center of the dipole is very, very large as compared to the dimensions of the dipole. So in such a scenario, r can be considered to be very, very large as compared to a for short dipole. In that case, a square can be neglected in comparison to r square. If a is very small, then the higher parts of a would be still smaller, and hence it can be neglected when compared to r square. So r square minus a square may be approximately equivalent to r square. Therefore, net potential for a short dipole at a point on the axis would be given by P over 4 pi epsilon. R square minus a square can be written only r square. So this is it. So you can observe For a point charge, potential varies inversely as the distance of the observation point from that point charge. But for an electric dipole, it is varying with distance as 1 by r square. So that's a very important point to be noted down. So this was the article regarding the expression for the electric potential at a point on the axial line of an electric dipole, right? Let's discuss the second one. Equatorial line of an electric dipole. Again, we are aware of it. Electric dipole is a system comprising of two equal and opposite charges separated by finite separation. This can be considered to be the center of the dipole. Dipole length is 2a, so this will be a, this will be a. Right perpendicular bisector, that's the equatorial line. This is the equatorial line. Observation point P can be considered to be over here. Its distance from the center of the dipole can be considered to be r. Okay, join these two. So this is r, this is a. So it's a right angle triangle. So this distance will be r square plus a square and square root of this term. This distance will be also equal. So it will be r square plus a square to the power half. It can be considered to be 1. It can be considered to be 2. Now, net potential at point P, obviously, at any point on the equatorial line, it will be given by potential at point P due to first and due to second. Now you can easily observe, due to the positive charge here we will have positive potential, due to the negative charge here we will have negative potential of the same magnitude, because the magnitude of charge is same, the distance is same. We can verify it mathematically. Look, V1 is the potential at point P due to this charge, so it is K, that is 1 over 4 pi epsilon, charge is positive, Q, distance is r square plus a square, it's square root, plus V2 is the potential at point P due to this charge, negative charge. So minus Q over 4 pi epsilon. Again, the same separation, that is r square plus a square to the power half. So it is equal to 0. So therefore, what we conclude is the electric potential at any point on the equatorial line, due to an electric dipole is always 0. It is because at any point on the equatorial line, the observation point will be equidistant from these two equal and opposite charges. So that is why the net potential would be 0. So these were the two articles. Now let us recapitulate some important concepts which we have studied till now. Now you can prepare this chart. Look, we have discussed electric field and electric potential for a point charge as well as for electric dipole, So this is physical quantity. You can prepare this chart. This physical quantity will consider electric field, and electric potential. Electric field and electric potential. We'll discuss this variation with distance basically. And this may be considered to be a point charge. It is electric dipole. And third, it's an additional topic. Anyway, you can write it over here. Electric quadruple. Electric quadruple. It is a system comprising of two electric dipoles. I mean, it will constitute two pairs of electric dipoles, right? So, just check the variation of these two quantities with the distance. Suppose r is the distance of the observation point from the center of the dipole or from the source charge. In case of point charge, electric field varies with distance as 1 by r square. In case of electric dipole, electric field varies as 1 by r cube. Following the pattern for electric quadruple, it will vary with distance as 1 by r cube. Electric potential due to a point charge, wherever k cube by r, so it varies with distance as 1 by r. Electric potential at a point due to an electric dipole, at any point on the equatorial it is 0, but on axial, at any point on the axial we have discussed, it is 1 by r square. It varies the distance as this. So following the same pattern for electric quadrupole, it will vary the distance as 1 by r cube. So getting the relationship, it is nothing but it can be derived from this particular expression, minus dV by dr. So any numerical in which suppose potential is given, electric field can be calculated, or vice versa. If the variation of electric field with distance is given, then the potential at a point can be easily calculated only by using this particular formula. These relations can be easily derived from this formula. I'll derive in the case of suppose point charge. Let's derive it. We know that for point charge, electric field varies as r square for point charge. So what to do is, it can be written as C divided by r square. C is any constant, right? So we know the value of electric field. Let's find out the value of potential. So dV would be equal to minus E dr. So V would be integration of E dr. Value of E can be substituted as C by r square. So if you solve it, minus C constant, 1 by r square dr. Now look, integration of 1 by r square is minus 1 by r. So what do you get is, minus minus get cancelled. Again repeat, integration of 1 by r square is minus 1 by r. Minus minus get cancelled, we will be left with this. Or V is proportion to 1 by r. Got it? So if the electric field varies with distance as this, then the potential must vary with distance as 1 by r. This is what we have proved. Similarly, you can prove for electric dipole as well. So this is a very, very important relationship, right? If the value of potential is given, then the electric field can be determined, and if the variation of electric field with distance is given, then the value of potential at a particular point can be easily sorted out, right?